I will present our study about the characteristics of LPG detonation wave propagation behind porous media model. LPG air mixture enriched with oxygen is usually used for generating heat in industry sector. However, it is possible that LPG oxygen will mix and react independently, and the mixture could generate detonation wave. This condition could harm people, environment, and piping system. Thus, detonation quenching to generate safety becomes very important. Detonation mitigation, also known as detonation quenching, can be defined as the transformation of detonation wave to less harmful deflagration wave. Mechanical methods can be achieved by inserting a flow obstacle in the combustion pipe. In the present work, LPG detonation transmission and reinitiation using a porous media model with two values of mass were studied. The stainless steel porous media model was used to a consideration of high thermal conductivity and abundant availability. Furthermore, initial pressure of the mixtures are varied from 20 kPa to 100 kPa, while the initial temperature is set constantly at room temperature, about 25 degrees Celsius. The detonation wave would propagate through the porous media model. Meanwhile, the conditions in the upstream and downstream of the model were also recorded. The facility consists of a horizontal circular cross-section detonation test tube with a diameter of 50 mm and a total length of 6 meters. The test tube consists of two sections, 1 meter in length driver section and 5 meter in length driven section. It is also featured with a dam tank to absorb the reflected shocks. The sections are separated by Mylar film with a thickness of 50 micrometer to prevent mixing between gases of each section. A spark plug was installed at the upper end of the driver section to ignite the combustion inside the tube. The porous media model was inserted in the driver section at position 5 meters from the spark plug. There are three different types of mixers used in these experiments: hydrogen oxygen mixture, LPG oxygen mixture, and LPG air mixture. The driver section was filled by a stoichiometric hydrogen oxygen mixture at a consistent initial pressure of 100 kPa and room temperature 25 degrees Celsius. On the other hand, the driven section used LPG as the fuel and types of gas as the oxidizer, air and oxygen. Initial pressure of the mixture inside the driven tube were varied from 20 kPa up to 100 kPa with an interval of 10 kPa. Both LPG air and LPG oxygen mixture were set at the stoichiometric conditions. All mixtures were premixed inside mixing tanks at least 12 hours to ensure the homogeneity. The filling of tube and gas mixing processes were controlled by a high precision digital pressure sensor. The properties of porous media can be seen in the table and from the pictures. When LPG and air were simultaneously mixed and ignited, there was no detonation generated from the combustion of the stoichiometric LPG air mixture in the pipe without porous media. Deflagration of the LPG air mixture was observed from mixture at an initial pressure of 60 kPa to 100 kPa. The combustion of LPG air mixture only generated deflagration wave instead of detonation wave, while the LPG oxygen mixture with initial pressure of 20 kPa to 100 kPa could generate detonation waves. Therefore, only the LPG oxygen mixture becomes a focus in this present work. The first mechanism was the detonation reinitiation, defined as a condition when the detonation wave was quenched after passing through the model, but the detonation wave was able to reinitiate far downstream of the model. This mechanism was observed from the combustion of the hydrogen oxygen mixture at an initial pressure of 20 kPa with a porous media mass of 15 grams. Data from pressure sensor and ionization probes of the condition is shown by figure. The vertical axis corresponds to a non-dimensional pressure P per P0, while the horizontal axis corresponds to time. Time arrival and pressure of shock wave are indicated by the rise of P1, P2, P3, and P4 signal, whereas the time arrival of the flame front is indicated by the decrease of the ion probe signal. It is also indicated that in the upstream of the porous media model, the flame front was detected by ionization probe 1 and 2. At the same time, with the shock wave detection by the pressure sensor 1 and 2. On the other hand, the flame front was detected in downstream of the model with some time lag behind the detection of the pressure wave. Hence, hence the detonation occurred in the upstream of the model while the propagation occurred in the downstream of the model. Calculation of data from pressure sensors and ionization sensors give actual downstream flame front velocity and shock wave pressure of 626 meter per second and 255.86 kPa in downstream of the model, which are much lower than theoretical GG velocity and pressure 2322 meter per second and 726.02 kPa. The track record inserted in downstream area is shown in the figure. Detonation cell started from a distance of 320 mm behind the model, which was far behind the location of the sensors. However, in this location of detonation reinitiation, there was no sensor installed. Thus, the pressure of shock wave and the velocity of flame front propagation and shock wave propagation of the reinitiating detonation could not be calculated. To summarize, the detonation propagated in the upstream of the model was successfully quenched after passing through the model. However, it was able to reinitiate at 320 mm behind the model. The second mechanism is detonation transmission, defined as a condition when the detonation wave were transmitted directly after passing through the porous media model. The example of pressure and the prime propagation history of the detonation transmission phenomenon is displayed in figure, which shows data from the combustion of the mixture with an initial pressure of 80 kPa using 20 grams of porous media. It is shown from the figure that at relocation of sensors, the flame front was detected at the same time with the detection of the shock wave. That indicates that a detonation occurred of a relocation of the sensors in the upstream and downstream of the model. A calculation of the data from pressure sensor and ionization sensors gave the actual velocity of the flame front and pressure of shock wave 2,259 meter per second and 3,086 kPa in downstream of the model. These values are almost reaching the theoretical GG velocity of 2,387 meter per second and GG pressure 3,856 kPa. The shoot track record of the experiment is displayed in figure. It shows that the downstream of the porous media model, the detonation cell started to appear at a distance of 18 mm from the model, which indicates the detonation was generated immediately behind the model. The figure displays the relationship between the actual flame front velocity and theoretical GG velocity to the initial pressure of the mixture. A close observation of the figure indicates that the actual flame front propagation velocity for every initial pressure was slightly lower than the GG velocity at the same initial pressure. Close observation of the figure illustrates that the detonation reinitiation distance is shorter as the initial pressure of the mixture increases. The initial pressures of the mixture directly influence the flame front propagation velocity. Thus, it also affects the velocity of the pressure wave emerging from the model, which corresponds to the energy transmitted by the flame in the downstream of the model. As the velocity of the flame front increases in the downstream of the model, the energy transmitted by the flame front after emerging from the model is increased. Thus, the time needed for detonation is to reinitiate becomes shorter. which means the reinitiation distance of detonation also becomes shorter. The conclusion is detonation reinitiation was recognized when the detonation wave was quenched after passing through the model, but was able to reinitiate far downstream of the model. It was indicated by the high value of the reinitiation distance of detonation in the downstream of the porous media model, more than 40 millimeter. This phenomenon was observed for mixture with an initial pressure of 20 kPa and 30 kPa for 15 gram porous media, and for mixture with an initial pressure of 20 kPa to 40 kPa for 20 gram of porous media. Detonation transmission was a mechanism when the detonation was transmitted directly after passing through the porous media model. It was indicated by the low value of the reinitiation distance of detonation in the downstream of the porous media model, less than 40 millimeter. This mechanism was observed for mixture with an initial pressure of 40 kPa to 100 kPa for 15 gram porous media, and for mixture with an initial pressure of 50 kPa to 100 kPa for 20 gram porous media. Under the increase of porous media mass, the addition of 5 gram, the reinitiation distance of detonation behind the porous media model also increases. However, uh, however, the distance of the distance significantly increases only for mixture with low initial pressure. Thank you.